Okay, so in the previous video, we talked about deriving the derivative of x squared, and I told you that actually we do not need to do this sequence of steps, right, for most functions. And the reason is because we have rules for differentiation for a lot of functions, and calculating the derivative of a function just amounts to applying these rules in a bunch of sequence of steps, and yeah, that will usually get us the answer. So the first rule is that is linearity, which means that the derivative of two functions when added up together, right, is just the sum of the derivatives. So the derivative of the sum is the sum of the derivatives. So what this means is that if I have a function f of x and g of x, and I add them together, that forms a new function, right? However, if I take the derivative of the new function, the new function's derivative is equals to df over dx, right? The derivative of f plus the derivative of g. And yeah, that's the addition. That's linearity for derivatives. Another rule is that if I scale a function up by some constant amount c, right? This needs to be constant. It cannot depend on x. If I scale a function up, right, by a scalar, then the derivative of that function, the scaled up function, is just the scale factor times the derivative. And yeah, so that wraps up linearity. Next one is polynomial. So polynomial, it tells me that derivative of x to the n, where n is some constant, right, is equals to n times x to the n minus 1. So just now, remember, we had the derivative of x squared, right? And we derive from first principles, right, using the graph and the approaching x plus h thing. We use the graph to derive that this is 2x. But actually, we see that that was just a special case of this polynomial rule. And this polynomial rule is, you see, n in this case is 2, so the answer is 2x to the n minus 1, which is 2 minus 1, which is 1. This is just 2x. You can see that instead of going through the first principles method where we do a long sequence of steps, we can just do it in one step by applying this polynomial rule, right? So with that, we can actually attempt to calculate the derivative of the following three functions. So the following three functions I'm going to talk about is this. So x to the 4 plus 2x, plus x squared. The derivative of that is just the derivative of the individual component of the individual functions, right, x, right? And the derivative of this can be performed by the polynomial rule. So x to the 4, the derivative of x to the 4 is just 4x cubed, and the derivative of x squared is just 2x. So that's the answer for the first question. Now for the next one, what's d over dt? Where did t come from? Fret not, right? This just means that I've relabeled the representation of the function. Remember that a function, we usually denote it as this: f of x equals to, let's say, 5 sine t, 5 sine x, right? But I could very well have labeled the input of the function by a different symbol, and the function still behaves the same way, right? It accepts a real number, and it plugs in the real number into the expression, the analytic expression, and it calculates a value, and it outputs a number. So when I take derivatives of a function, I'm always taking derivative with respect to the parameter inside the function. So in this case, if I have this f of x, okay, perhaps it's best if I denote the second function g, so I don't get confused. So we don't get confused. For the first function, right, it makes sense to say df over dx. The x in the denominator is the parameter of that function, right? The symbol represent the parameter of that function. In the second case, it makes sense to say dg over dt, right? It would not make sense to say dg over dx, because g takes the symbol the g takes in is t, it's not x. So that's just what this is saying. So d over dt, 5t plus 3, right? The rules apply. So linearity tells me that this is d over dt, 5t plus d over dt 3. So dt, so this would just be 5 d over dt t, right, where we use the scaling rule, and d over dt 3. Now t is a polynomial where the power is 1, so if we take d over dt of t, it's just 1 times t to the 0, which is just 1. So this is just 5 times 1, right, which is just 5, plus, what is 3? Where did 3 come in? 3 is actually a polynomial. 3 is x to the 0, right? Or rather, 3 is t to the 0. So if we take d over dt of 3 t to the 0, 0 comes down, and 0 times anything is 0. So derivative of a constant is 0. So the derivative of that function is just 5. Okay? So lastly, see that this is the derivative of 1 over x. 1 over x, even though it's not a polynomial, but you can write it as, you can think of it as the power of minus 1, and the polynomial rule still applies to negative powers. It in fact even applies to fractional powers like square root. So this is just minus 1 times x to the minus 2, and this is just minus 1 over x squared. Now these examples that I'm going through, they're not useless. Most of them we actually see them appear very soon, right? For example, derivative of 1 over x, right? This appears in gravitational potential energy. So I'm not making you suffer for nothing, right? These are very real applicable examples of derivatives of functions that we are used in physics. Okay, so yeah, that's for the first 3 rules. So we have linearity and we have polynomial, and now let's talk about trigonometry. How do you take derivative of trigonometry functions? Trigonometry will come in very useful when we talk about things like oscillations, because it turns out that nature really likes sine and cosine functions, and we'll talk more about this when we talk about differential equations. They're actually very natural solutions to differential equations. So trigonometry, derivative of sine is cosine, derivative of cosine is minus sine. Okay, exponential, another very natural rule that appears in physics, right? Derivative of e to the x is e to the x. So this is the only function where the derivative is itself. That's quite funny when I first learned about it. Okay, next will be product rule. Derivative of a product of two functions, fg, right, is just f g prime plus g f prime, right? These rules are just rules that you memorize along the way. You get used to them. Lastly, chain rule. If I compose two functions, this one is it's okay if you don't get it right at first, but you get used to it very, very soon. If I compose two functions, then the derivative of the composite function, right, is just the following. So I'll talk more about this when we come to the examples, because the examples are very naturally lend themselves with these rules. Okay, so let me just bring these examples to have a bit more space. So derivative of sine 2t, right? We see that sine 2t is actually a composite function. Sine 2t is actually a composite function. The first function is actually, okay, let me just move these down. Right. So the first function, in this case, f, is actually f of y equals to sine y. And the second function is actually y of t equals to 2t. So I'm going to go through this very detailedly, in a great detail, just for once. If this is a bit slow, I apologize, and please just stick with me so that I can just go through this right once. So the derivative of this function is actually d over dt of f of y of t. Can you see that? right? We substitute in y of t into the following f of y, and derivative of sine 2t is just, substitute this in here, is just derivative of composite function. So what does the composite function rule tell us? It tells us that we have to write this as, the answer to this is df over dy over dt, right? Where in this case we had x over here, but x is just a symbol, right? In this case we replaced x with t. So these two functions can be easily differentiated, right? df over dy, this is f of y. df over dy is just cosine of y. And dy over dt, y of t is just this, right? dy over dt is just 2. So it's just the product of these two functions. In other words, 2 cosine y, and that gives us 2 cosine 2t. So it takes a while to get used to this, but I would just recommend spamming a lot of practices. And basically the idea is that if we take the derivative of sine of something involving t, but it's not t alone, then basically what we got to do is we got to pretend this parameter in the function, right? This parameter in the sine, this argument that we put into the sine is the thing that stays as kind of like one object, right? So this 2t remains inside, and then we differentiate sine to turn into cosine. And then after that, after we're done with that, we multiply that by whatever the derivative of this inside guy is. And in this case, the inside guy is 2. So, the inside guy is 2t, the derivative is 2, so that's why we multiply by 2. It takes a while to get used to this, but it becomes very natural after a while. So the next natural example of the chain rule is this. So let me just move this down a little bit again. So you see that this is actually composite of two functions, right? The first function is f of y equals to e to the actually in this case it's actually composite of it's actually composite of two functions, right? And the next function is y of t equals to 5t, sorry, minus 5t, right? So you take the derivative again. This is just df over dy over dt, and this, if you work it out, it give us minus 5 e to the minus 5t. Okay, yeah, this derivative of this type of function, this appears in things like RC circuits, resistor capacitor circuits, which appears in SJPO. And it also appears in things like natural decay. We talk about nuclear physics. Lastly, we have d over d tangent x. Oh no, tangent didn't appear in these set of rules. So what can we do? This is actually a bit more involved, right? I'll be honest, tangent doesn't really appear much in physics. Actually, it does. I take that back. So derivative of tangent is derivative of sine over cosine, right? Sine of x, but instead of writing over cosine, right, I'm going to write cosine x to the minus 1, right? Then basically we apply product rule. First layer is product rule, so that will give me cosine. Product rule is, if we look at over here, is the following. So that will give me sine of x, derivative of cosine, minus 1, plus cosine of x to the minus 1. Right, when minus 1 is to the power of minus 1, it's just 1 over cosine. And then derivative of sine, which is cosine. Okay. Yeah. So so this is sine x, right? And then this is actually a application of chain rule again. So this is going to be minus 1 over 1 over cosine squared x. And then on the numerator is minus sine x. Yeah, so I actually applied chain rule followed by the polynomial rule, yeah, I actually applied the polynomial rule followed by the chain rule followed by the polynomial rule, and the end result is this. And the other one is just going to be 1. And this is going to be sine squared x over cosine squared x, right? Plus 1 and sine squared x plus cosine squared x over cosine squared x equals to sine squared plus cosine squared is known to be 1 over cosine squared x. Sometimes we write this as secant x squared. So the derivative of tangent is secant squared. Yeah, so when you go to Sec 3, you're going to learn a lot of these rules, and you're going to have a lot of practice with them, but these are important in physics. So yeah, study your calculus properly. So that's the exercises, and we're coming to the end of derivatives, but before that, I'm going to talk about maximum and minimum in the next video.